Hello everyone. In evaluation of composite characteristics, what we have already discussed the characterization of matrix material and characterization of reinforcing material. Now, we will discuss here the testing and characterization of composite material. So, before testing we must know the mechanisms of failure in composites, then only we can understand the requirement of different test techniques. So, during its life cycle, a composite is subjected to different forces and it can withstand some forces and some other forces which damage its structure. So, the following incidents are observed when a fiber reinforced polymer composite fails. These are the incidents through which the fiber reinforced composite fails. It is by matrix cracking, fiber pull out, fiber bridging, fiber matrix debonding and fiber rupture. These are the different mechanism, different processes by which a matrix can fail. So, we must understand, we must know this phenomena and we must know how to test or how to characterize the matrix to know all these processes. So, nature of damage can be by in plane damage, by micro buckling, by delamination or by buckling delamination. So, these are the different natures of damages. The main issue in composite is that it is made of two entirely different components and their addition is very important. It is not a homogeneous material, it is a heterogeneous material. So, this in plane damage, micro buckling, delamination, buckling delamination we must understand. So, out of plane stress leads to delamination because the fibers do not contribute significantly to the strength in that direction. This is delamination, it is out of plane. Like we have made composite, very good composite with the fibers aligned in the this length direction. This is the fiber alignment direction and say these are the matrix component. If we apply force in this direction, the matrix will show very good characteristics, but as there is no fiber in the this direction, this say y direction, cross plane direction. So, once we apply this force in this direction, this matrix may get delaminated. So, although fibers are there in that this direction, due to this force, out of plane force, this matrix will get damaged This process is known as delamination. Next is that compressive buckling. So, compressive load can lead to micro buckling of fibers. So, once the compressive load is applied, so this micro buckling of fibers take place, because this reinforcing fibers, they cannot compress lengthwise axially, whereas the matrix can get compressed because of their higher elasticity. So, that result micro buckling. So, this is one of the reasons of composite damage, composite failure due to high pressure. Compressive load also leads to microscopic delamination buckling. So, delamination buckling, especially if the material contains pre-existing delamination region. So, in this zone there were some delamination there. That is why due to compressive load this delamination buckling took place. These are the failure mechanism. So, composite laminate tests are tensile characteristics, bending characteristics, impact properties, compressional behavior. Here we are talking about the axial compression, fiber matrix bonding, which is very important as far as the tensile load distribution is concerned, interlaminar strength characteristics, viscoelastic and dynamic properties, density and void content. Void content is very important. We must know the void content. Ideally, there should not be any void present in the composite. Presence of any sorts of void deteriorates the quality of composite drastically. Now, as far as ASTM D3039 test, this is actually specifically for tensile testing of fiber reinforced composite. It suggests at least 5 specimens has to be taken. The specimen dimensions are given here, where tab is required of certain thickness. This tab is required to protect the material from damage from applied load during testing, because there will be jaws. If we do not provide tabs, then the matrix may get damaged. This is tab region, tab length, and tab is attached with the that composite by adhesive. So, tab is required to increase the area of loading region and thus reduce localized concentration of stress. So, using tab, the total stress is divided into it is actually distributed to the larger area throughout the width of the specimen. So, it results reduction in local stress concentration. So, as per the standard, the strain rate should be selected so as to produce failure within 1 to 10 minutes. The properties here can be measured that ultimate tensile strength, ultimate tensile strain, tensile cord modulus of elasticity, Poisson's ratio, tension transition strain. Now, tensile failure, if we try to see the modes of failure in composite, it is not like the data of tensile strength of two composites may be same, but we must also understand the way it fails during tensile loading. Similarly, for compression, for even bending, we can get this type of mode, and this mode of failure shows the detailed by knowing this mode, we can predict the characteristics of failure or nature of failure of composite after applying say tensile load. The mode is expressed in terms of 3 letters. The first letter, which shows the failure type of failure, and second letter, it shows the area where failure took place, and the third letter, which is showing the location of failure. Let us see LIT, what does it mean? L in first letter means lateral, this is LIT, it is a lateral failure, okay. It is not along the direction of load, it is across the direction of load, that is a lateral, this is the failure zone. I means inside grip, it is the at the grip, inside the grip point, here this is the failure point, and location of failure, it is at top, T is for top, here it is a. So, LIT, by knowing that term, we can guess it has taken place inside the grip, the type of failure was lateral failure, and it has taken at top jaws, okay, top of the samples. Now, we have to decide whether this data we would like to take or not. If the failure took place inside the grip, that means there was some problem in the grip, we have to reject this data. Similarly, GAT means G means here from the first character at a grip. So, it took place at the grip point, not in between the jaws, it is at the grip point, and failure area is also at the grip and at the top grip. That means, it is expected that there was some problem with the top jaw, top grip. So, we can reject that also. LAT, lateral, A means at grip, T means at top. So, in this way we can get idea. DGM, D means edge delamination. So, you can see here it has taken place during tensile loading, edge delamination took place. G means at gauge, means between the grip point. So, there is no problem with the grip, and M means at the middle location. So, in addition to the numerical value, we can get idea, we must get idea about the type of fracture, type of failure takes place, because in the composite we must know the type of failure. If it is taking place due to delamination, that means we have to improve upon the delamination process. So, here it guides us the way to improve the manufacturing process. So, we can see different other mode of failures. Let us see XGM. What does it means? X means explosive, suddenly it broke. So, this is the explosive. G means at gauge, in between there is no problem with the grips, and M is at the middle. So, if we see SGM and say AGM, A means angled, G at the gauge and at the middle. So, from these two, only difference is that here it is a explosive, suddenly it broken, and here it is little bit in angle form it has broken. So, from this mode, these two modes of failure, even if the composites they have the similar or same failure value, the stress at failure value, still we will get some idea about the internal structure, or we can predict the performance of this composite. So, these are the different photographs of flax polypropylene composite after failure, tensile failure. We can see in untreated flax composite, the failures are not straight failure, because of the fact that there were less bonding between the flax and the polypropylene, but once we treat the polypropylene with MAGPP, the bonding improved and we can get sharp breakage. So, load carrying capacity has improved, and here we can see the fiber slippage took place. Next testing is that compression test. Here we are not talking about the cross plane compressive property which we use for fabric testing. Fabric testing we cannot do in plane compression because of the flexibility, and in composite the in plane testing is although important, but in plane composite testing is more applicable here, because once we use composite in load bearing purpose, the loads are placed or applied on composite in plane direction, but in textile fabric loads are applied in cross plane direction. That is why in composite in plane compressive properties are important. This method is most appropriate for composite material reinforcement by high modulus fiber. Now, let us see. So, this is a textile fabric, it is flexible and we apply load in cross plane direction. But in composite, in case of composite, if we say use this is composite material. If we use in plane compression, this will little bit compress and will not get idea about the usability, about its performance in long run. But if we apply load, so this is say composite material, if we apply load in plane direction, in that case that there will be loading here, and this is specifically used for high performance fiber, where tensile strength is very high, but if it fails due to the matrix, because as we are applying using high performance fiber here, tensile strength will be very high, but the compressive characteristics here mainly depends on the matrix material and also on the matrix and fiber bonding. So, that if it is very strong in tensile direction, we must know, because in tensile direction the load is carried by this high performance fiber, but once it is compressed in plane direction, the load is not there on this high performance fibers, load is mainly carried by the matrix material. So, that is why in case of composite we must test for in the in plane compression. So, this is used for high modulus fiber or high, say carbon composite or Kevlar composite, we must use this technique. This test produce induced compressive force, and the specimen, actually it is specimen, it forces into the specimen through shear at the wedge grip interface. So, the test result is influenced by test fixture characteristics, test method sensitivity, specimen preparation, how do we prepare specimen, thickness and gauge length. If we change the gauge length, the test result will change, type of grip, edge effect, okay, in the angle ply laminate. So, these are the different factors which affect the test result. So, in this picture if we see, this is the composite sample specimen, okay, and here these are clamped, this is specimen, and this is the top jaw, upper jaw, and this is the lower. This is basically it is a upper jaw, lower jaw, and once it is coming down, okay, they are coming closer, the compressive load, the in plane compressive load will be imparted on this specimen, and we can test this, we can get the compressive strength value, minimum number of tests as per standard it is 5, and sample dimensions are given here. Compression test specimen thickness depends on the gauge length, expected compressional strength and longitudinal modulus. So, the thickness of the composite we have to change depending on these parameters. So, we can get the results in terms of ultimate compressive strength, ultimate compressive strain, compressive modulus, Poisson ratio, these are the parameters. Again, if we see the compression, the type of failure is also important. Here the first letter, first character, it is a mode of failure. Second is the failure area similarly, and third is the location of failure. Now, here the compressive failure is expressed in terms of TAT. T means here transverse shear, this is transverse shear. A means at grip, this is at the top, and T is the location, it is at the top. That means, here compression, compressive failure has taken place at the top grip, and it is at grip, and it is transverse failure. Okay. Let us see next one, BGM. B, it is a brooming, its brooming effect means it is a buckling has taken place, delamination has taken place, so that it forms a broom like structure. So, brooming due to compression, and brooming takes place due to say very poor interface between matrix and the reinforcing material, and also the poor quality of reinforced matrix. Even if we use very strong, very high modulus fiber, this if this brooming type of failure takes place, then we cannot use this. So, this type of failure will not occur during tensile loading. So, for high performance fiber, that is why compressive failure is important, compressive testing is important. So, BGM brooming has taken place, G is at the gauge and M is at the middle portion. So, looking at the failure type, we can take decision, we have to adjust our process parameter, we have to change the matrix characteristics, quality of matrix. So, HAT, H means it is a through thickness. So, this is through thickness, it has taken place, A at grip and T as the top. So, this way we can get all this type of failure. SGV, long splitting at gauge and at various point. Okay. So, so long splitting took place. So, these are the different failure characteristics, there are many other combinations can take place. So, this is HAT is GV. So, we have other characteristics. Now, these are the failure, here earlier you have discussed these are the failure which are acceptable failure during testing. Actually, these are the failure if it take place, then we can get actual idea about the performance of the composite and we can take preventive measure. But these are the failure which are non acceptable in terms of compression failure, like DTT, delamination tab adhesive at top. So, here in tab adhesive during testing, tab adhesive delamination took place. So, which is not actually the failure due to the composite characteristics, it is due to the testing technique, like throughout thickness, inside grip at top, this is the throughout thickness, here HIT inside grip. If the failure takes place inside grip, that means there is no problem with the composite, it is a problem with the gripping, DIT, delamination inside grip. So, inside grip there is some problem. So, if the failure takes place inside grip or due to grip, we do not accept that failure. These are the failures. These failures will not take into account, will reject the result. Next is the bending testing or flexural testing. It is as per ASTM D7264. We take 5 specimen. If we see the unlike tensile, shear or compression, the flexural failure is not the basic material characteristics. They are actually combined effect of tensile, compression and shear. Once we take the flexural testing, once the composite bends, either tensile or compression or shear takes place. So, while bending at outer side, the tensile test takes place. Let us see here. Now, this is a composite. Okay. When it is bending, this outer side it is a tensile, this is compression, and in between there will be shear. Okay. Now, while testing, we can reduce shear to some extent by readjusting the, say this is the thickness, and here if we bend, this is bending, this is the length of the specimen. So, length and thickness ratio if we change, we can readjust or we can manipulate the shear component. So, typically what we try to reduce the shear component by readjusting the selecting the L by T ratio, but during bending tensile failure or compression failure takes place. Suppose the compression tensile strength is low, that means it will fail at this zone. Compression strength is low, so it will fail at this zone. So, this is indirectly it shows the that flexural testing, it actually it is a combination of tensile, compression and shear properties. When a flexural load is applied to the specimen, all 3 stresses are induced. Material failure is dictated by which of the 3 basic stresses is the first to reach its limiting value, that is strength. As I have mentioned, if tensile strength is low, it is reaching at fast, so it will fail immediately. If compressive low is low, strength is low, it will reach at fast. But the understanding of flexural testing is complex, but the testing it is very simple. Okay. So, if we perform, so here it is a testing method. So, to simplify the test, stress strain in the specimen, shear stress component is minimized as I have mentioned. So, there are 3 components. So, shear stress we can minimize, this is done by the support length and thickness. So, L by T ratio, if we increase L by T ratio, we will reduce the shear stress component, okay, and only the tensile and compressive stress is there, and shear stress independent of specimen length, while bending moment, that is tensile and compressive stress, is directly proportional to the specimen length. So, if we increase the length, that will affect the tensile and bending stress. Now, there are two types of flexural testing. One is 3-point loading system. What is 3-point loading system? Here there will be two support points and another is the external loading points from the top, and another is a 4-point loading system. There will be two support and two external loading point. So, 3-point loading consists of a support point near each end of the beam and one load point at the middle, okay. And 4-point loading here, two support points, and these are typically, this distance between two loads are typically 1/4 of the this total length of the composite. In general, the mechanical strength measured through 4-point bending is lower than the one we test in the 3-point test. So, this here in at 4-point testing, mechanical strength we get lower value. So, this is the stress and strain. Now, let us see, P is the breaking load, okay, and L is the span length, H thickness of the specimen, B is the specimen width, and delta is the deflection at center. So, if we keep all these parameters same for 3-point and 4-point bending, we will see this 4-point bending stress is lower than 3-point bending, whereas strain in 3-point bending is higher than the 4-point bending here. So, strain is higher and here stress is lower, okay. Next property is, which is very important property, it is a impact property. Impact property of the reinforced composite sample can be evaluated using either pendulum type impact testing machine or drop weight impact testing machine. So, pendulum type are of two types typically used, IZOD impact test method and Charpy impact test method. So, IZOD as per ASTM D256 or ISO 180. So, the IZOD impact is defined as the kinetic energy needed to failure the initiated fracture. So, to initiate fracture and continue fracture until the specimen is broken. So, there will be fracture initiated. So, then we will measure the total kinetic energy, the notches are created. So, to prevent deformation of the specimen upon impact. So, here if we see the system here, IZOD impact testing, what we do here, this is composite with notch created. And another impactor, normally just let us draw here. notch is created. So, there will be one impactor, pendulum type impactor, which is used for typically we can see in case of tear strength, element of tear strength, that type of pendulum is used, and once it is released, this will have impact on this upper side. Here this side is gripped, this side is gripped, and this will impact, this will have impact, and the failure will take initiated will be initiated at this point, because it has notch has already been created and the failure will take place. So, the specimen is clamped into the pendulum impact test fixture with the notch side facing the striking edge of the pendulum. The pendulum is released and allowed to strike through the specimen if breakage does not occur. So, in case of breakage, it is a very strong material, in that case we can increase the weight of the hammer. So, here this is the support, strike height we can adjust, and here is this is the impact direction. This is it is after swinging it will have impact. So, all these dimensions are important. Okay. This is the sample specification, standard specification here, striking point, the upper tip of the specimen, at this point the striking will take place, and the data which we get is impact energy and impact strength. So, these are the data we get, and notch angles are it is a 45-degree angle. Okay. And here this photograph shows the specimen after IZOD impact testing. This is the type of failure it takes. So, here you can see it is a notch was created, after that failure took place here. Okay. Another technique is the Charpy impact test method. This test was actually it is a ASTM E23 or ISO 148, originally developed for the materials and later it is extended to composite, dimension 55 by 10 by 10 millimeter. Each specimen contains 45-degree angled notch on the other side, okay, of the loading, striking point at the middle of the sample. So, here this is the striking point, amount of energy absorbed by the specimen, that is the data. So, another test is the drop test by ASTM D7136. This test method determines the damage resistance of the multidirectional polymer matrix composite. It is a laminated form. Okay. This is showing the impactor. Flat rectangular composite plate is subjected to an out of plane concentrated impact. Okay. So, potential energy of the drop weight is defined by the mass and drop height. So, we can change the mass of this impactor and height of this impactor, and there will be a free fall and it will impact on the composite material. The specimen dimension 150 mm by 100 mm and thickness is as per the specimen. So, the damage resistance property generated by the test method depends on the specimen geometry, impactor velocity, layup, impactor force. These are the different parameters which will affect the test result. So, we have to keep all these parameters standard. The damage resistance is quantified in terms of the resulting size and type of damage of the specimen. As we have already seen earlier, the damage size is also important. The damage response is a function of the test configuration. These are the different types of damages: depth depression, split or crack, combined. So, these are the different types of damages during the impact testing. So, fiber matrix interface bonding is also important. So, we must know it is very important as far as fiber reinforced composite. So, we must study, we must know the fiber matrix interface bonding strength. So, there are basically 4 different types of principles or mechanisms of bonding between fiber or reinforcing material and matrix. One is, this is the adsorption and wetting. So, that means the matrix material will get adsorbed and wet the reinforcing material. So, that type of bonding take place. Mechanical keying is also one of the mechanisms where the rough surface of reinforcing material is created. So, that there is a mechanical bonding, mechanical keying take place, which enhance the bonding strength. Chemical reaction between reinforcing material and the matrix, and electrostatic attraction. So, electrostatic attraction is one of the methods where we can get the matrix adhered to the fiber surface. So, bonding strengths can be controlled by coupling agent that we have already discussed using one experiment using MAGPP. Silane coupling agent is one such agent which improves the bond strength. So, we can increase the bond strength by coupling agent. The bond strength can be measured by different techniques. These are single fiber pull out test, single fiber push out test, fiber push down test, full fragmentation technique. The following assumptions are made during the interfacial bond strength measurement: no shear strain in the fiber during pull out, no shear strain is taking place, no transfer of normal stress across the fiber end. So, normal stress is not getting transferred to the composite or adjacent fibers. These are the basic assumptions. Now, in single fiber pull out test, one single fiber is gripped, this is the fiber is gripped, and here is the composite is gripped here. It involves pulling a particularly embedded single reinforcing particle fiber out of a block of matrix. This is a matrix block and one single fiber has been placed. So, debonding debonding can take place, propagation of debonding and frictional sliding. It takes place in 3 stages. At first debonding starts, then this debonding propagates throughout the interface, then frictional sliding will start. So, that will give us idea about the interfacial bonding. The drawbacks of this method are the interface of the specimen may differ from those in real material, as different degree of constants are imposed in absence of neighboring fibers. So, that is basically it gives us one idea, because in actual composite there will not be a single fiber, there will be many other fibers, there may not be 100% complete covering by the composite material, that is matrix material. there will be other interference of neighboring fibers, there will be difference in manufacturing techniques. So, the technique gives a rough idea, and it is very difficult, it is difficult to carry out specially thin brittle fiber. So, thin fiber and which is brittle in nature, we cannot use this technique. Single fiber push out test, again here we prepare composite and then we prepare in the slice form. This here it is showing one width of the slice or thickness of the slice. This thickness is very small, maybe in terms of millimeter or few millimeters, and then the fiber, this is the fiber is pushed against the matrix material which is gripped here, it is pushed out and this distance is very small, and during pushing again the debonding and all this will take place and the fiber becomes displaced, so that it protrude from the bottom of the sample, it is displacing here, debonding has started from there, then it has propagated and then fiber, then sliding, frictional sliding took place. Main drawback here is that we cannot use this technique for very fine fiber. Fiber with larger diameter we can definitely use. Fiber push down test, here again in push down test bulk fibers are taken and that will be, that is pushed down by applying force. So, this leaves a permanent displacement between top of the fiber and the top of the matrix, and that we can get idea about the interface. Another technique is the full fragmentation technique. This method is used for mainly metal matrix composite, sometimes polymer matrix composite. Now, we can see here typically the for fibers with very high modulus fiber we can use where extensibility is less. This is the matrix, and if we see these are the fiber, this is fiber. Now, once we apply load, once we apply axial load, if the bond strength is high, then the fiber will fragment like this. But if the bond strength is not high, the fiber will not break and there will be extension on the composite or matrix material. So, that by knowing this length ratio we can get idea about the bond strength. This method is used for mainly metal matrix composites, and we can use this for high modulus fiber. This method involves embedding a single fiber in the matrix and straining matrix in tension parallel to the fiber. As I have already shown, fiber fractures, fragment into pieces, aspect ratio exhibits by the fiber segment are measured. So, if the fiber does not damage, does not actually break, we can get idea that there is less bonding strength. Okay. Also, next parameter is that void content, which is very important. The void content is actually higher void content deteriorates the quality of the composite drastically, and void content is by measuring the density of material. Experimental density is measured by experimentally, then we can measure the theoretical density. This is the theoretical density, by knowing the density of matrix and density of fiber and volume fraction, and fiber volume fraction we know these things. So, from there we can calculate the void content. So, void content is the from where presence of actual voids that we can get to know, and which actually deteriorates, higher void content deteriorates the matrix quality to a great extent. So, we will stop here. In next segment we will discuss few testing techniques which are non-destructive in nature. Earlier techniques we have discussed, all the specimens are destructive in nature, and what we have seen, though for those we have to prepare specimen and test, but there are some situations where we cannot take out the matrix material during use application. If we want to test whether there is any damage, whether what are the characteristics there, those we can test only by non-destructive method. So, non-destructive testing of composites we will test in the next segment. Till then, thank you.